Welcome to the second module of this DTrace training. This module is titled Going Further, and there's a good reason for that. After some preliminary remarks, I want to cover DTrace variables and functions, followed by aggregations. That's a very important feature in DTrace, but the bulk of this module is going to be about 3 examples where I really want to show you not only the kind of things you can do with DTrace, but also the methodology behind it. How do I get to those DTrace programs as I'm showing them? Because that's what you eventually need to learn, to use DTrace to sort of guide you in a certain direction and develop your D programs as you follow that path. In this second module, I want to introduce new functionality and features, hence the name of the module Going Further. That's definitely what we're going to do. We're going to explore a lot of features in DTrace. But it will be largely example driven. I'm just going to show you as many examples as I can. However, at times you will have to read the documentation. There's an excellent user guide that will give you the details that I'm going to skip, the fine print to make sure that you get it all right. So please get your copy of the guide, the link is on the next slide, and use that to your advantage. You probably also want to look into man pages of functions you want to trace. It's included in the example section. I'll show you the kind of information that you're looking for. And in rare cases, you may want to look into the source code of whatever you're tracing. That could be the kernel, when you're doing the kernel tracing. But it could also maybe be for a library or the application, because sometimes that level of detail can make the difference because it tells you what to really probe for. This is definitely recommended reading. The Linux DTrace user guide, the link is given here. It's an excellent document and it has so many details and examples as well. I can't stress it enough. I will say it again throughout the training. This is the document that you need to have open while you're working on your DTrace programs. DTrace command is very extensive in terms of options. There are many. I'm not going to cover all of them. I selected a couple of the most common ones, or the ones that I use most of the time, better said. But be aware that there are many things that you can customize when using DTrace. In the first module, I showed you the -L option to list all the probes. There's also a -Q option so that DTrace is in the quiet mode. It won't print things by itself. If you're tracing a command, you use -C and then the command that you want to trace. In case you read your D program from a script, which I can highly recommend, you use the -S option. In case you're tracing a running process, you can give the PID through the -P option, the process ID. And there's a whole category of options that you can access under the -X option. With that, you can sort of specify your preferences, and there are 3 different types of options. Compile time options, where you can customize the compile part. Recall that your D program is compiled into eBPF code, and with these options on the DTrace command, you can customize things. There are also options to customize the behavior of the DTrace command itself. And the third category are options that are specific to the D program. In a way, that's why you set your preferences. And here are 3 examples of how you can use that -X option. The first one, zero defs, zero definitions. What that means is that you can get the message that there's no match for the probe that you have defined. But maybe that's fine. Maybe you're just in the development phase and you're sort of playing around. You don't want to be bothered by that. You certainly don't want to remove that from your D program because you know you're going to get back to it later. This is a great option to tell DTrace, don't worry, it's fine. You can, for example, restrict the tracing to a particular CPU. Well, I only want to know what happens on CPU 1. At runtime, you can get indentation. The entry and return probes are indented as you go down the call stack. So in that way you can sort of see the flow of your program. It tends to produce a lot of output, but it can be useful. In any case, there are many options, and check the user guide for all the choices that you have. In addition to command line options, you can also put in the Pragmas directly into the code. You have the same set of choices. The syntax is also more or less the same. You place them in the D program and that's it. You use the Pragma D option syntax and then the option optionally with the value depending on what you're using. So in case of my zdefs option, I use Pragma D option zdefs and I put that into my D program. So whenever I have a probe that doesn't have a match, it's fine, it's being ignored. The D language is a programming language, and with that come variables, just as in any other programming language. And in DTrace, you can create variables explicitly by declaring them. We give the data type, in this case an integer, but there's also string and other types. So you can explicitly declare that variable, or that's what I use all the time. You leave it up to the decompiler to figure it out. In this case, I'm assigning an integer value to this variable, and that automatically makes it an integer variable, and I don't have to worry about any declaration. The D language has various types, scalar variables like I was just showing, an integer, a pointer, and those are the scalars. You can also have arrays. Most common use is a single-dimensional array, but it can also be multi-dimensional. The D language also supports associative arrays where you have a collection of elements and you retrieve them with a key. And here's an example. I have an associative array called myArray. The key has two fields, a string and an integer, and I use that to access elements or store elements into that array, just as you would do with associative arrays in other languages. What's also common in other programming languages is the scope of a variable. Simply said, that's where a variable is visible. That's where you can read and write the variable. And the D language has three variable scopes: global, clause local, and thread local. Now, thread local is going to be skipped in this module. I will cover that in a future module. So we're going to focus on global and clause local variables. Variables are global by default. If you don't specify anything further, a variable is a global variable. Exceptions are clause local and thread local. And I'll talk about clause local in a minute. The key thing is that a global variable can be read and written by any probe at any time. So you have to make sure that happens in a controlled way, the way you intend it to be. They're absolutely useful, but there's this catch that any probe can access them. Clause local variables are much more restricted because they're local to the set of clauses executed for a particular probe firing. What does that mean? You have a probe. The probe can have one or more clauses. The clause local variable sort of lives in those clauses. It doesn't exist outside of those. When the probe fires, the value is undefined, so you need to make sure that it gets an initial value. It's like an automatic variable in some other programming languages. A clause local variable also ceases to exist after those clauses for the fired probe complete. It literally doesn't exist anymore. They're really meant for local access. So why would you use them? Performance and local scope. Faster access because, for example, to access the elements of an associative array could be costly. You can store an element in a clause local variable, and from there on you have faster access to that variable. You can also avoid name collisions. Let's say you have a global variable called x, and for some reason in your probe you also want to use a variable x, but that should not be the same as the global one. Well, you make it clause local and you're good to go. And this is how you do it. Global variables are the default, so you don't have to do anything, and they are initialized to 0, so that's convenient. They're not thread safe because anybody can modify them at any time. A clause local variable is defined by a keyword, this and then an arrow. That makes the variable a clause local variable. Again, it's not defined initially, but it is thread safe. And you'll see examples of this very shortly. In this program, I'm going to show you the difference in behavior between the global and clause local variables. And my examples are self-contained programs, so there's always a part that is fixed. That's the first 4 lines here. They've already been covered in the first module. I'm not going to talk about that anymore, but just that they are there because I'd like to show full program. What we see, we have the begin probe. The begin probe initializes 3 variables, A, B, and C. var A and var B are global variables because that's the default, and they get initialized to 10 and 20 respectively. C is a clause local variable and it gets the value 30. What we have is that there's another clause to the begin probe, and that updates variable C. That's fine because it still exists. We're part of the same probe still. And that's why I split it this way to make that clear that it doesn't matter in as far as the scope of the clause local variable goes, it's available. And then I have 3 print statements. Further in the program, I have some probes. And the first one, for example, updates A. That's fine because any probe can read and write the global variable A. And the same for B. So both are updated whenever that clause executes. This is also where you see things may get tricky because you got to be sure that that happens in the right way. But it works and it's very useful. And in the return probe, I print the variables as well as in the end probe, just to see what the values are. So we start with the initial value. A gets the value of 10, B is 20. C, when we print it, that's in the second clause of the begin probe, is 60 by then because we did the update. Now C is not available outside of the begin probe, but in the fclose return probe we're going to print A and B. Meanwhile they have been updated and they have the value 11 and 21, and that carries over to the end probe, so they are accessible throughout your D program. In addition to our own variables, the DTrace also has built-in variables and quite an extensive list of variables, and they're very convenient. The user guide has a full overview of what's available. Here I'm showing a couple of examples. The arguments to a probe are stored in an array with the name args, and you can access them through indexing into that array. These are the typed arguments. They have the data type. What I like to use is the short version. That's for the first 10 arguments, which is typically sufficient. And they're always an integer, a 64-bit integer, and you cast that to whatever data type it should be. I just find that easier and more elegant, but of course the choice is yours. The thread ID is always accessible in a variable called TID. Now wherever you are, you can get the thread ID. We've seen $target in the first module already. That's technically a macro and it expands to the process ID of the target that is traced. In that way you adapt to the situation, and I really like it. You'll see me using it all the time in the example section. DTrace has a set of functions and are very convenient. There's quite an extensive set of functions available. Again, check the user guide for an overview. But there are functions for data recording, string manipulation, copying of data, aggregations, and many, many other things. Very convenient and to use, and recommended to check the user guide. I now want to talk about aggregations. They're really important in DTrace. They're very powerful and very flexible. An aggregation reduces many data values into a compact aggregate. For example, the minimum of a set of numbers. You start with that whole set of numbers and it's reduced to a single number. An aggregation structure stores the result of an aggregation function. And aggregations in DTrace, they start with the @ symbol. So as soon as you use an aggregation function, you're going to store those values into an aggregation, and that starts with the @ symbol. As shown here, I have my aggregation. I'm using the minimum function, the min function. That makes this an aggregation, and I use the @ symbol. You don't have to use an index into the aggregation, but you can. It's like an associative array. And you can have a key with multiple fields. Here I'm showing there are 2 fields, 2 strings, and I can store and retrieve my elements using those values. In this case, string A and B. The functions themselves, the aggregation functions, they could take one or more arguments, and the value that's passed in becomes part of a set where the function is applied to. To save memory, we do that immediately where possible. That's kind of one of those optimizations in the implementation, but to us what matters is that the set is sort of built up along the way and we apply the function to it. For example, here I'm summing up the elements of whatever comes in, and I use the sum aggregation function for that, and I store the results in an aggregation called DTotal. You will see lots of examples along the way. These are the aggregation functions that you have at your disposal: the average, the count, increment the counter by 1, the maximum value, the minimum value, the sum of all the values passed in, the standard deviation, and there are 3 very interesting aggregations that I'm going to demonstrate later on. They show you the frequency distribution, and you can choose for 3 different representations, either using a power of 2 scale, a linear scale, or a log linear scale. The choice is yours, of course. But what it does, it allows you to have incoming data and you can sort of visualize the distribution of that, and that's incredibly powerful. You can print aggregations. You don't have to do that because by default all the aggregations are printed at the end. So before the program stops you will see all the values. But you can also take matters in your own hand in a way, and there's a function called print A that is used to print aggregations. It takes 1 or more aggregations as input, and optionally there's a format string. The format string is used to print the fields in the key and the value. And what you do is you use a printf style formatting for the key and similar for the value, although the value you need the @ symbol in the format. And here's an example. I have an aggregation. Clearly the key consists of 2 fields of type string, so I use %s and %s for those fields. The value is an integer. If it wasn't an aggregation, you would use %d, but this time it's an aggregation, so you use the @ symbol as well. And in that way you can control the output. And I'm now going to cover those examples. I've collected 3 examples. They are designed to illustrate what I just talked about, plus quite some additional things. And the way it's organized, there's a specific question, and we're going to see how we're going to use DTrace in order to answer that question. And I'm going to show you the fully worked examples, the full code, nothing hidden. You could use those and get started. And I'd like to see that as a starting point, not the end line. Use that to explore whatever you want to do. Another goal I have with these examples is to show you the DTrace way of developing your program. Because it's very often an iterative process. You cast a wide net first, but not too wide because you don't want to probe everything going on in your system that would cost you performance. But you're not yet sure what you're looking for, so you use some wildcards to figure out, get a feel for the landscape, and then you zoom in on the areas of interest. That's the typical DTrace way of doing things, so these scripts evolve. You may write another script to really get some details. It's all up to you, but be aware it's an iterative process and you start wide and you zoom in. Before I go into those examples, I want to talk about the provider that I'll be using in the first 2, the PID Provider. The PID Provider enables me to trace entry and returns to functions, userland functions. You can also trace instructions by giving the absolute address or function offset. In this case, I'm not going to do that. I'm going to just focus on the name of the function. But it is really very powerful to know when you get into that function and when you leave, and take action while you're there. Just a little technicality, each process has its own associated PID provider. For example, when you have a process with process ID 123, you have the PID provider PID 123, and likewise you could have PID 456. And that brings me to my favorite. What I like to use is the $target macro in the PID provider, because that automatically expands to the process ID of whatever I want to trace. So I don't have to worry about that anymore. and everything will be adapted. The first example is quite lengthy because I want to show you the whole process from start to finish. And what we're going to do, we're going to trace I/O calls in an application. And we're going to use the PID provider to give that information to us. The test program, it doesn't matter what it's doing. That's one of the beauties of DTrace. What you will realize is that whatever I'm showing is sort of independent of the details what the application is doing. I want to know something about that application. Well, DTrace will give me the hooks to actually get that. And what the application is doing by itself, it doesn't really matter. In this case, it's reading from a file. That's an input parameter when executing the program, and that's it. We don't know what it's doing. But what we do want to know, which files are in use and how many bytes are being read and written. And as a bonus, can we get a count how often the relevant I/O functions are executed. We're going to use the PID provider, as I just said, and we're going to design probes for the common functions in libc that open, read, and write a file, because that's what we're interested in. And we're going to heavily rely on aggregations, for example, to get a function call count, but also for other things. And we're going to print those aggregations using the print a function. Now, if you don't explicitly print aggregations, or you use print a without changing anything by default, the output is sorted by the value. But in this case, we want to have the output sorted by the function name, and I'll show you how you can change that behavior of print a. This is our first D program, and this is a fully working program. Here we see new elements. First of all, at line 4 and 5, I enable the sorting and I set it to position 0. That means I want to have the print a sort by the first column, and I will make sure that my aggregations have the probe func as the first element. That's my responsibility. I have my probes, line 7 to 9, and I'm using wildcards in the function names because I'm casting that somewhat wide net. It's not that wide because I'm restricting the module to libc. If I would leave that out, I may get other functions that match that name, but in this case I'm focusing on libc, and I use the PID $target as I explained earlier. And we're going to use the entry probe. And whenever that probe fires, we're going to store the function name. The module name is like a little extra. I added that for demonstration purposes. We don't need it because we know the module is always going to be libc. But in general, you'd like to make your probes a little bit more general so that you have more flexibility, just in case things change. But again, it's a little bit overkill here. I just wanted to show it. And what we're going to do, as soon as one of those probes fires, we're going to increment the count. In the end probe, we're going to print the results. That's quite common. You don't have to do that. You can print within probes as well. But here we have collected the data and now we want to print it. So at line 15, I print some sort of diagnostic line, the candidate functions. Then I'm setting up 3 columns in a table that I want to produce using printf. And at line 17, I'm printing the aggregation. And the format string has been chosen to reflect that I have 2 strings in the key, and the value is an integer, and I use the fixed width so that I have a nice table. I run my program. I have my D program stored in a file called io.d. I use the -c option to specify the command, and that's it. Then when the probing has finished, I get this output, I get my string, the candidate functions, and I get a list of all the files that matched the probes, the ones that fired. I sort them by name, and the reason I did that is that I now can see those functions with starting with an underscore or double underscore. They're typically internal functions that at this point I don't care about. It's good to know what's happening, but I don't care about it. I care about the higher level functions. We see the module, we know that was libc, and we see the count. And I'm going to zoom in on those 5 functions shown there because those are the sort of the user level functions. Those are the ones visible. And I'm going to focus on these 5. Well, what does that mean, focus? In DTrace, that means I have to write probes to get more information out of those functions, and that's exactly what we're now going to do. The first function on the list is fopen64. That's the large file version of fopen, and that's the one that we're going to probe. Be aware that fopen in itself may call open, and we'll actually see that later on. You check the man page to find out which arguments it have and the return value, and this is what we see. And we can leverage that the first argument is the same for both functions, it's the name of the file. The return value is different, it's a pointer versus an integer. And with that, we can write the probing part for these 2 functions. They're given at lines 7 and 8. We use the wildcard, we want to see everything with fopen, I'm just sort of lazy here. And then I define my aggregate at line 10. The name is files opened, it has the probe func as the first field in the key. And then I'm using what I mentioned a little bit earlier, I'm using arg0. Arg0 is the first argument, that's the file name. Since it's in arg0, it's passed in as a 64-bit integer, but I can use a conversion function, like in this case string of, to convert it to a string. So my aggregate has 2 strings in the key, and it's simply counting how often they are called. I also want to probe the return, because the return of those functions will give me the file descriptor or the pointer, depending on the function call. So in this case, I cannot reuse the clause as I did on the previous slide. I have to write 2 different clauses, one for each probe. But they're very similar. At line 14, I have an aggregate that stores the probe func and arg1. Arg1 is the return value of the probed function. And seemingly, at line 18, I do the same. That's true. But when it comes to printing, I need to know whether that arg1 is a pointer or an integer, because that's different depending on the call, and that's why I have 2 aggregations. As we've seen before, I do the printing in the end probe, and it looks quite similar, I think, as what we've done earlier, but there's a difference here at line 26 and 27. The print A statement is quite similar, but remember that second field in the key was either a pointer or an integer, and that's reflected here. At 27, I print a pointer, %p, and at 27, I print an integer, %d, and I use a fixed format. Don't have to do that, of course, but that makes the layout look nicer. And this is the output. What we see the various open calls and the file name, it's opening, and the count. And what we see, there are 2 temporary files. That's interesting. Apparently, this application uses temporary files. We also see that it looks like it's opening the same file twice. Well, that's not really true, because internally the call to fopen eventually results in open being called, so that's why the name appears twice. In the second table, we see the pointer and the file descriptor. So for fopen, we see the pointer, and for the 3 open calls, we get 3 numbers, the different file descriptors. And they're called once. So we've covered that part. Now we're going to look at how many bytes are being read and written. Again, check the man page, and we find the PWrite function that was one of those functions in the list that we want to explore. And what we see, it has the various arguments, and what we want to know is the file descriptor and the count, how many bytes have been written. And the man page also tells us that PWrite on a successful return returns the number of bytes written, and that's a number that we're interested in. In DTrace terminology, it means that the entry probe needs arg0, the first argument, the file descriptor, and arg2, the byte count. The return probe needs the return value, and that's always stored in arg1, so that's one that we need for the return probe. And that gives us the following probes. At line 7, we have the entry probe. We store the result in an aggregation. The aggregation has 2 fields. arg0 is the file descriptor, so we use that to differentiate. And then we're using an aggregation function called sum. Remember, the byte count was in arg2, and we're just summing it up. So this will give us the total number of bytes written on that file descriptor using the PWrite function. In the return probe, I wanted to show you something else, how you can actually use those aggregations to do nice things for us. Because now the aggregation definition only uses probe func. So I'm gathering all the information for, in this case, PWrite. And what I'm doing, I'm summing up all the values of arg1, and that was the return value, was the number of bytes actually written. So what this is going to give me, this is going to tell me exactly how many bytes PWrite altogether has been writing. And that's a very common use of using aggregations in DTrace. The print statement, pretty straightforward. And this is the output that it produces. We see the function PWrite. It's using file descriptors 6 and 7, and in both cases it writes 4 bytes on it. And in total that was 8 bytes. Now, of course, that's really simple, but if the I/O was more complicated, we would still get that information out of our DTrace program. We also need to trace the read calls. And what we're going to do is we're going to use aggregations. Again, it starts to hopefully look similar. In the read entry probe, we're going to store the probe func and the number of bytes that are being read in an aggregation defined at line 9. And what it's doing, it's using arg0, that's the file descriptor, as a differentiator into the aggregation. So we have two values, the probe func and the file descriptor, and it stores the value of the number of bytes that are being read accumulated as we're calling the read function. So this accumulates everything that's being read into the file descriptor stored in arg0. At line 10, I have an aggregation and it looks similar, but there's a big difference here because I'm not using a second argument. It only uses the probe func. So this collects everything that's being done by the read function. And it's collecting all the bytes that are read. So it's summing up just as the other line. But now it's no longer differentiated according to the file descriptor. In other words, this gives me the grand total of all the bytes that are being read by the read call. In the return probe, I use a similar approach. And I know the number of bytes actually read are stored in arg1, and I'm summing them up. So that gives me the number of bytes that are actually read. And because the key is the same, when we print those aggregations, we can actually print two aggregations in one print A statement. And that has the advantage that we get the side-by-side printing. We can directly compare those numbers. And that's what happens at lines 22 and 23. Recall the key is the probe func, so we start with the string, the %s fixed format to 10, and then we have two aggregation values, one for each aggregation. And with that, we get the following output. The first two lines are from the entry probe, and what it does, it will show us for each file descriptor, which is only one in this case, how many bytes have been read. The second block will show us the grand totals regardless of the file descriptor, again, which is in this case only one. But in general, when you design your DTrace program, you want to have that flexibility just in case multiple file descriptors are used. But the last one will always be aggregated over all the file descriptors. And what we see in this case is that the actual number of bytes read is less than what's being input. So we see there's this mismatch that the number of bytes that's being read according to the input into the read call is higher than what's actually being read according to the return value. But what's going on here? And my favorite approach is to add a print statement inside probes and start digging deeper, and that's exactly what I did. And here I'm showing you the code. I have the print statements at lines 9 and 10 and 16 and 17. They're quite similar. And this also shows a bit of the DTrace way of thinking because I'm printing probe func and probe name. But that's really overkill because I already know the function name is read and the name is entry. But that gives me more flexibility just in case I want to reuse this, or maybe I add another probe. In this way, I'm sort of safe, and it's a more robust way of coding your DTrace program. But in this case, what I'm really interested in is how many bytes go in. That's in arg2 in the entry probe. And in the return probe at lines 16 and 17, I'm printing arg1, which is the return value. That is the number of bytes that have actually been read. So with these two print statements added, I get the following output. And what we see, they nicely match. The entry and return values are the same. They seem to be multiples of 4096. That's no surprise. That's the page size is 4 kilobyte. But the difference is in the last pair, where I try to read 4 kilobyte, one page, and I only get 712 elements. Well, that's no surprise in a way, because I'm reading from a file, and it's not said that the number of elements really matches the page sizes. So there's a gap. But what it shows is the strategy is to read at the page size level, and at some point at the end there may be a mismatch, but that's all part of the design. There's nothing to worry about. So we're okay. The reason I wanted to show you this is the kind of information you can get quite easily with DTrace. It shows you what happens under the hood, but nothing to worry about. The last thing left to do is to write a probe for the fread function that's being called. But what I noticed was that the arguments for fread and fwrite are the same. And with that, we can write one clause for both. And what we're going to need in terms of DTrace is arg1, arg2, and arg3. arg3 has the file pointer. arg2 has the number of elements that are being read or written. And arg1 has the size, and the size is the number of bytes per element. And with that, we can get all the information. On the return probe, we see that both of them return the number of items that are read or written. And in this way, we can have one clause, and that will make our code more general. And that's what I'm going to show now. I have my probes at line 7 and 8. I'm probing on the entry to fread and fwrite. And at line 13, I have my aggregation. But what I want to show you here is how I can customize the aggregation. The second field is a string that I build up in lines 10 to 12. I know probe func is either fread or fwrite, and I can use the simplified, the shortcut if statement. Regular if statements are not allowed in the D language, but this one is allowed. So depending on whether probe func is fread or otherwise it will be fwrite, I construct a string. And then at line 12, I'm going to merge that string. I'm using the strjoin function with the probe func, so I have a little mini sentence. It will be read from by fread or written to by fwrite. And that's going to be the second field in my key. The first field is the third argument, and that was the file pointer. Then I compute how many bytes are actually read or written. I sum them up, and that's it. And in that way I get the total byte count in this aggregation. The return probe is pretty straightforward. I know that this function call returns the number of elements that are read or written, not the total byte count. And that's stored in the aggregation at line 17. I have my print statement. Hopefully by now that's all clear, but I also want to show you how you can use that to customize your output at line 21. It starts with onStream. And remember, the first field in the key was the pointer, so I print the pointer, then total bytes, and that's actually my constructed string. So we'll say total bytes, read, and so forth, or write, depending on what I have constructed, and then I print the value. And that will give me output like this, onStream, and then the pointer, the total bytes read from by fread is that number. And I get the total elements that are read as well. That's the return value. In reality, you would put things together. You would have a full D program. It would have all the probes that I have talked about. The end probe will contain all the print statements. So you put it all together. Be aware you can always put print statements in probes as well. Here I consolidate everything in the end probe. And the output is a combination of what I've been showing before. I'm only showing the last part. I won't show the file open and what files are opened and the file descriptors and so forth. This is the overview that I was looking for in terms of reading and writing a number of bytes, and this exactly tells me what has been read and written. In the second example, I want to trace malloc and free, and I'm going to use the PID provider to find out more about the memory characteristics of an application. The test program that we're using here repeatedly calls malloc and free. It allocates a block of memory, it will use it, and then release it. The parameters to the program are the number of blocks that you want to have and the minimum and maximum size. It's allocating 64-bit integers, so that controls how many bytes are being allocated. Optionally, you can give a percentage of blocks that are not released, and that sort of gives you a memory leak, and I will show you how that works out with our D program towards the end. The question is, can you show the memory allocation statistics of this application? For example, show me all the sizes that are allocated plus the minimum and maximum. And this is the D program that we wrote to answer that question. At line 5, we are probing the malloc on entry. The aggregation at 7, you've seen it before, we're just counting how often that function is called. But this is a new one at line 8. I'm using one of those functions that returns a frequency distribution, and I'm doing that on the arg0, that's the input into the malloc. In other words, that's on the number of bytes that are requested to be allocated. And that will tell me, give me an overview of the range of values and their distribution. Incredibly useful function. At lines 9 and 10, I'm just taking the minimum and the maximum, so I know the smallest and the largest size. Then at line 12, we have the probe to the free, the entry. That's a very straightforward one by now, I hope. We're calling how often it's called. And at line 15, we have an aggregation that stores arg0. Arg0 is the pointer to the block that needs to be freed, so we're collecting those pointers as well. I also want to show you 2 more probes that I added, and that's for demonstration allocation sort of purposes. The first probe is at line 17. It's the regular entry into the malloc, but this time I'm using a predicate. That means this probe will only fire if the condition in the predicate is met, and the condition says that the block size that is requested has to fall between 1 kilobyte and 4 kilobyte. And in case the probe fires, I'm going to create my frequency distribution, this time in a linear scale. It's going to be on the block size on arg0. And again, for demonstration purposes, I'm going to restrict the range from 2K to 3K with an increment of 256 bytes. So it's going to show us a subset of what comes in, but the nice thing about this distribution is that it will also show me the lower and the upper bin, so I have all the information displayed. And in that way you can really control and zoom in and get narrower and narrower. The second probe, well, we know that the malloc returns a pointer. Upon successful execution it will return a pointer, and that's stored in the return probe in arg1, and I'm going to use that as a field in the key to my aggregation so that I know which addresses have been returned by the malloc. And this is all printed in the end probe. It's a pretty large one. I think most of it is quite straightforward. The new element here is that at lines 40 and 42, I'm printing those frequency distributions. It's stored in the aggregation, so all that I need to do is print the aggregation. And as I said, and if I don't do that, the system will do it for me. But I would like to have some explanation, and that's the printf at lines 39 and 41. That's what they're doing. And with that, I get the following output. I'm running my test program, and what I'm using here is 500 blocks. The minimum is 100 and the maximum is 10,000, so I specify the range here. It tells me that I have calls to a thing called C-free and malloc. Now, I didn't ask for C-free, I'll get back to that in a second, but it tells me that free and malloc basically were called 501 times. That's because I have some support structure that I need in the test program, so that gives me an extra malloc and free pair. The smallest block allocated, the largest block allocated are shown here, so you know exactly what happened there. And then I'm showing the addresses of what was allocated and what was freed. And of course they should match, and they do. But what's really interesting is here I'm actually allocating 500 blocks, and I see that only 4 addresses are being used. Clearly the system recycles memory addresses, and that's because I'm freeing. I'm allocating, I use it, and then I free it, so the next malloc can decide to reuse that address, and that's clearly happening here. Now on the previous slide we saw cfree, not free. Cfree is another function to free memory, and this could happen when multiple symbols have the same address, and that's why we see cfree and not free. The frequency distribution, this is a log2 scale. What we see on the left hand side under value are bins. So we have a bin from 256 to 511, then a bin from 512 to 1023, and it shows you how many items you have in that range, in that bin. And that's also symbolically represented with the @ symbol. That's scaled to fit on the screen, but it quickly tells you where possible outliers are, for example, and what the distribution overall looks like. Really useful for all sorts of purposes. Then we have the linear representation, and this is what I mentioned. We see the underflow and overflow bin marked by the arrow in red, so we know like what's to the left and to the right of the distribution, but we also see the details of the distribution itself, and that will give us a very fine-grained view into the memory allocation process. There's another experiment that I wanted to share with you. This test program allows me to introduce memory leaks, and I did that. That's the option -L, and I set it to 50%, so half of the allocated blocks are not freed. And we see that's reflected in the output, because now, and I'm only allocating 10 blocks by the way, otherwise we've got a long list of addresses. So I'm allocating 10 blocks and 50%, so 5 of those are not freed. And that's what we see here, because now we don't see that reusing of addresses because they're not available, because free has not been called. And this is all completely expected, but I want to show you how the same D program gives me this information as well. And that's really the goal of writing a D program. You write it so that anything that shouldn't happen will show as well. And this is a simple example of that. And that brings me to the third and last example in this module, the scheduler. We're going to use the PID Provider to see what the operating system scheduler is doing. The test program implements a matrix vector multiplication that has been multi-threaded using POSIX threads or P threads for short. The question is, can you tell me how often this program is scheduled to run on the CPU and taken off again? The PID Provider is really the one that is going to give the answer to the question that was just asked. So after 2 application examples, we're now going to look at the system, and potentially you could go system-wide if you wanted. The PID Provider supports 7 probes, and one thing I wanted to show you, the -P option on the DTrace command, because with that you can select a certain provider, as we're doing here for the PID Provider. And we see those 7 probes. The names I think are fairly straightforward. In any case, I want to focus on the on CPU and off CPU. And I'm going to count how often they are called, because on CPU is when the program is ready to go and run on the CPU, and off CPU means it's taken off the CPU. And the question was, how often does that happen? Note that for this example to work, you need DTrace 2.0.2 or higher. And this is my program. I'm using the PID Provider. I have my probes at line 5 and 6 on CPU and off CPU. And I have a predicate. If I didn't have the predicate at line 7, and you've seen it before, it selects only the process ID of the target process that we're monitoring. If you wouldn't do that, you would go system-wide. That'll work. You would see all the occurrences of on CPU, off CPU. But that's not what we're interested in. We're interested in the particular behavior of this application. But again, without a predicate, you would get all the occurrences. And also here, I'm customizing the aggregation at line 11. I have a clause local variable called state. And depending on whether I'm on CPU or off CPU, It includes a certain string, and that's the key in this aggregation, and I'm just counting. At line 16, I'm printing that. And the first part is the key, that's my comment string, and then the second one is the count, and that's an integer. I hope that by now this is fairly straightforward. And this is the output. I run my D program, I give it the application that I want to monitor. I'm running, and at the end it tells me that this program was scheduled on the CPU 14 times and taken off the CPU 14 times. Now, I selected this example because it's about multi-threading in a way, although we didn't look into the details at all. There's going to be a future module where I'm going to look into multi-threading in all sorts of details, both at the DTrace level and at the application level. So stay tuned for much more extensive coverage of this. You'll see much more of the PID Provider as well. I hope this has been useful. I hope that by now you have a good understanding of how you develop a DTrace program, the kind of things it can do for you. It can do a lot more. There's going to be additional modules for that. But for now, I would say good luck writing your D programs, and thank you.